All right, hello, Algebra 2 students. Appreciate you finding some time in your home life there to get online and do your notes. Okay, we're getting to a next section of notes. One of the things you need to do at this point is we need to conclude the Cornell notes from the previous lesson. So what you need to do is you need to take a moment, probably pause the video. You need to come up with a summary to go along with the lesson that we talked about on the basics of functions. So that will probably involve rereading the notes real quick, kind of getting basically an idea how to summarize it in 1 or 2 or 3 sentences. Doesn't have to be a paper or anything like that, but you do need to do your summary. After you've done that, you can come back to the video, drop down a couple of lines, and we're going to begin a new set of notes. All right, these are for Monday, and on Monday we're going to be looking deeper into functional topics, and more specifically, we're going to be looking at functions from the perspective of dependent versus independent and discrete versus continuous. Okay, new lesson, new objective. Today's objective, okay, on your Cornell notes, the student will further examine the topics of dependence and independence and continuous and discrete. If you need extra time, press pause on the video. Then once you're ready to go, hit play again, and we'll move on. All right. Now, this is basically review stuff, so you may not need to write this down, okay, unless you feel like you need it. We've seen that x values and y values can have various names. So, of course, x's and y's. And we have learned kind of over and over again that the collection of the x values is referred to as the domain. Collection of the y values is referred to as the range. What we're going to see today is that there are actually a lot of different synonyms that go along with them, and we're going to need to be familiar with all of them. Okay, so another way that we're looking at focusing on today is the idea of independent versus dependent. You should have heard it before. If not, then you're hearing it for the first time, but I doubt it. Okay, the x-axis is what is referred to as the independent axis. The domain are the independent values for the function. Okay. The information that goes with the y-axis is what we call a dependent variable. And to put it in basic layman's plain English, we're basically saying that dependent depends upon independent, okay, or the value of y depends upon the value of x. As we progress higher and higher into mathematics, you're going to see more and more often that the x-axis is of more interest and more concern than the y-axis is. Okay, the x-axis is usually something that is it's kind of like a controlling condition of an experiment, or something that is driving some sort of an observation. The y-axis is simply a measurement of, hey, as this experiment or this observation goes on, here's the information that we found along the way. Okay, and that's pretty much going to be the case. The x-axis is more important, and the y-axis is there mostly for just some measurement. Okay. Now, we discussed the other day when we were talking about the basics of functions that if we have an equation of a function, we can plug in values from the domain and get the corresponding values from the range. As a matter of fact, when you're very first learning about functions, that's typically the way that functions are introduced. You plug in an x, you get a y. You plug in an x, you get a y. And if you ever plug in an x and get more than one y, as a result, then that is not a function. Okay, so one of the ways that we're kind of taught, and if you haven't heard it before, you're going to hear it now, is to think about the equation as what's referred to as a function machine. Okay, a function machine. And what this machine does is it changes values from the domain to the range. Okay, so to put it in kind of a cornball little diagram here, okay, we're going to consider a function. We're going to start off with a linear function, 2x minus 3. And we're going to pick some random values from the domain. I've chosen 2 and 4 and 7. Could have picked any values, positives, negatives, fractions, decimals, zeros. It doesn't matter. I just picked some small, whole, positive numbers just to keep it simple. Okay, and here is ultimately what happens. We end up with values going into our function machine, okay, into the equation. And we can pick any values we want. 2, 4, and 7 were just random choices. Okay, and one at a time, these values will find their way into the function machine, and the machine produces a result. So for example, the first value that we have, the 2, it is going to go into the function machine. Okay, the 2 will take the place of x, in which case we have 2 times 2, which is 4, and then when you take away 3 from that, what comes out of the function machine is a positive 1. Okay. Similarly, this can apply for all values. Our next value we're looking at is a 4. When a 4 goes into the function machine, 2 times 4 is 8. Take away 3, you end up with 5. Okay. 7 goes into the function machine. 2 times 7 is 14. Take away 3, you end up with 11. Okay, so this is how the independent-dependent relationship kind of works. Everything that the y does depends upon the value for x. That's why the x-axis is independent, y-axis is dependent. Okay, now getting to some of those synonyms that we were talking about. Okay, here's one that you're going to start bumping into a little bit more often. Okay, is the idea of a pre-image and an image. Okay, this vocabulary is associated with functions really pretty regularly. Okay, that the independent values in the domain are pre-images. Okay, and the image is the result of whatever that pre-image value in the domain, whatever the function does to that, it becomes an image. Other synonyms there, of course, x values, the collection of all x values is the domain, the collection of all y values is the range. That's review. Okay. And another thing that you will come across every once in a while is the idea of input and output. Okay, and that's kind of where I picked the little computer monitor idea from. Is typically we input data into a computer or into an equation, and then output comes back out of the computer or the equation in the form of some type of a result. Okay, so input and output are synonyms for what's going on with the x's and the y's. And then lastly, as we've said several times, the idea of independence versus dependence. Okay. Unfortunately, there's a lot of different synonyms, as you can see on the screen right now, and you will need to know all of them. You can't just say, well, I understand x's and y's and domains and range, so that's good enough for me. I'm not going to learn the rest of this stuff. The problem is I have absolutely no way of knowing when it comes down to a unit test or a semester test, ACT or SAT. I don't have any way of knowing what kind of vocabulary they're going to use. So you may know X's and domain. What happens if they pull out the term pre-image and you don't know it? Well, we just took a pretty easy question to answer, and we're now guessing at it because we didn't understand the vocabulary. Okay, so some vocab terms that you're going to need to commit to memory. The other distinction that we're going to make today is to discover the difference between the idea of discrete and continuous. And we've kind of touched on this a little bit here. So you should already, if you took notes on your review, you should already have these notes. But anyway, we're reopening the discussion. In simple terms, discrete means that there are gaps in the domain wherever you are looking. And we're going to look at that statement a little bit further. Okay, and continuous means there are no gaps in the domain where you are looking. And we're going to look at that statement a little bit further because the idea of discrete and continuous is a little bit bigger than we've let on so far. Okay, so let's just start with the simple stuff. Here's kind of what we do know about discrete and continuous. Okay, so we're going to look at these three graphs. You can press pause if you want a second to jot these down. And then we're going to go one by one from the left to the right, and we're going to answer whether we believe these are discrete functions or continuous functions. So press pause if you need to. All right, now considering the left-hand function, okay, the idea of whether it's discrete or continuous, okay, we're just looking really at the entire function itself. We're not set any boundaries. We're not told to look only in certain places. This function is what we can see. The question is simply, where the function does exist, is it complete? Are there any holes? Are there any missing pieces of data or anything like that? Well, it's pretty easy to see. When you look at this one, it is mostly complete. However, when you get to x equals 0 in the domain and look up, we see a point that is open. It is not included. There is a gap in the domain. We would have no choice except to refer to that function as discrete. How about the one in the middle? Again, we're not concerned with the fact that it doesn't continue all the way to negative infinity, okay? But look at where it is. When it does finally begin in the domain, does it exist completely? Are there any gaps in it, any missing pieces of information? Does not appear that anything is missing. Otherwise, we would have to see an open circle somewhere. So this one will be classified as continuous. Now, the last one's pretty obvious. This is the easy one to spot. Okay, when you look at these, obviously we only have 4 pieces of information in the domain existing between -4 and +4. Is the domain filled up entirely in between -4 and +4? Clearly not. So we would say that this one is discrete. Okay. Now, the more advanced thing that we're going to be looking at today, okay, so this is probably the biggest part that you're learning. Discrete or continuous can apply only to certain intervals. Functions can do a lot of different things, okay, especially functions that we refer to as being piecemeal, okay, or piecewise. And here is an example of such a function, meaning it is doing certain things in certain intervals, but then in other intervals it is doing something completely different, almost entirely changing its style, its slope, whether it's linear or a higher dimension, stuff like that. Okay, so we're going to use this graph, and we're going to answer whether we believe it is discrete or continuous on the intervals that are specified. Okay, and I've got several different ones that we're going to take a look at. So again, hit the pause button if you need a second to scribble some things down. Okay, let's start at the left-hand side here. Our first interval, what is it actually asking for? Okay, we're coming from -infinity to +4. Now, negative infinity, you notice it has the parentheses on there. Infinities are always considered to be open. So anytime you have the infinity symbol, you will have open parentheses like you do there on the left. Okay, the -4, it has square brackets. What are the little brackets used for? Okay, square brackets mean that it is closed, that that point is included. So we are only on this first interval looking from -infinity up to -4 in the domain, and 4 is included as part of the graph. So basically, if we wanted to, we could kind of draw in a line. Maybe should have done it a different color so it would have been easier to see. Okay, there we go. And we're only looking from -infinity, okay, up to that point, and we want that line to be included. Okay, so looking to the left of the green line, do we see any evidence of any points being missing from the domain? Does not appear so. So what does that make it? Discrete or continuous? Continuous would be our response for that interval. Okay. The next interval asks us to look from -4, including -4, up to 0, the origin, but the origin is not going to be included. So I'm going to put my line here. Okay, -4 is included, and we're going to 0, and 0 is not included. So I'm going to put a dotted line there. Okay, well, let's look in between those two lines. Do we see any evidence of the domain having missing values? Does appear so here at -3. When we look up at that point, we have an open dot. Okay, so there's a point in the domain that is not represented. So what does that make this graph? Discrete or continuous? This one would be discrete. Okay, I think you're probably getting the hang of it. Why don't you press pause for a second and see if you can't answer these remaining intervals, and then hit play when you're ready to go again. Okay, the next interval goes from -3 to +2, not including -3 or +2. And it's a good thing that those are not included. We've got this little wavy line graph going through there, but at the end points, -3, +2, we've got gaps in it, but nothing in between the intervals. So this one would be continuous. Hopefully you got it. Let's look at the next one. We're going from the origin to +3, including both of those locations. Okay. We see we have a major problem there at x = 2. Okay, the graph does split. It jumps in different places, and that's not the end of the world that it does split at -2, or at +2 rather, but it is the end of the world for this question because there is no value there at -2. So we would have to label that one as discrete. The next one from +2 to +3, including both of those locations. So there to there. Okay, well, again, we're going to run into the same problem as we did on the previous one. At +2, we are missing the end point. Okay, so if they'd have had an open on that 2 rather than a closed on that 2, it would have been continuous. But since they included the value x equals 2, it is discrete. And finally, we have from +4, not including 4, off to infinity. So let's have a look. Okay. Oh, wasn't supposed to be included, so if I really wanted to be exact about it, I put a dotted line, and then we'd head off to infinity. Does it appear that that is going to be the case? Yeah, we've got values beginning at and even including 4, and then of course we have the ray sticking off of that, indicating it's going to continue off to positive infinity. Looks good, so we would label that one as continuous. Well, that's the end of the notes for today. You need to have those ready to go with you on Monday. Bring them to class, and we will see if we can add some practice problems to go along with that so we can better understand independent and dependent and continuous and discrete. Appreciate you listening. Have a good weekend.